Hey, welcome everybody. So today we're going to start talking about percent composition and how we turn that into empirical and molecular formulas, okay? So the question is, how are percent composition, empirical formula, and molecular formula related? At the end of this, I would like you guys to write a summary. It can be written on one of the notes pages. Probably on the front would be the easiest. And on the front of the first page, I want you to answer that essential question after we go through the notes, okay? So let's start with percent. So most of you know what a percent represents, okay? It tells you what part of the whole something is made up of, right? So like the population is 50% boys and 50% girls, roughly, okay? So, you know, 50 out of the 100 of the population is going to be one gender or the other, okay? So that part out of the whole population is male or female. And it's kind of the same thing. I mean, anytime we do percent in chemistry, it's basically the same idea, okay? So when we do percent composition, it is the total element mass, so the mass of just the element, one of the parts, one of the elements, okay, over the molecular mass, the mass of the entire molecule. So the mass of the element part, one of the elements, over the whole molecule's mass, okay? That is percent composition. So it's actually very, very simple to do this, okay? We need to have two things. We need to have the element mass and we need to have the molecular mass. So the example here is calculate the percent composition of each element in ethanol, okay? Now for these problems, we're gonna go ahead and use a calculator, okay? So calculate the percent composition of each element in ethanol, and then the formula is given to you there. So if I look at it, I have two carbons, right? Carbon is 12.01, so this is gonna be 24.02. Since I have two of them, I have to double the mass of carbon from the periodic table, okay? Then we have 5 and one more hydrogen, so that's 6 total hydrogens, right? Okay, it doesn't matter that they're not all in the same place. If I have 5 here and one more here, I have 6 total hydrogens. So 6 times the mass of hydrogen, which is 1.008. Let me get my calculator. And I have 6.048. And then we have a single oxygen here, and that is 16.0. Okay? So those are the masses of each element in the compound. The total, if I add those together, 24.02 plus 6.048 plus 16, I end up with 46.068. Okay, now what I'm going to do is in the calculator, I am going to take the mass of the element, so I'm going to start with carbon, 24.02, and divide that by the total mass of the whole molecule, okay? And then, since it's a percent, we take that decimal and multiply it by 100. And so I'm going to leave 3 significant figures in my answers, so 52.1%, okay? So then it's the same process for hydrogen. I would take the mass of the hydrogen, so 6.048, and divide it by the mass of the whole molecule, 46.068, multiply by 100, and I get about 13.1%. So for the last element, I could do a couple of things. I could take 16 and divide it by that total and multiply by 100. Or I could realize that the remainder of this compound is oxygen. And all of the percentages have to add up to 100%. So if I know that, you know, with 100%, 52.1 of it is carbon, 13.1 of it is hydrogen, the rest of it has to be oxygen. So what is the rest if I'm trying to get to 100%? Well, let me go ahead and do some subtraction. So 100 minus 52.1 minus 13.1. So the remainder is 34.8. So that's what I've got left over. And that's going to be the percentage of oxygen. So it's a very simple process to find percent composition. It's just the element mass, and you have to take in consideration any subscripts, okay? So the element's mass divided by the molar mass of the entire compound, okay? All right, so listen, percentages can be converted into ratios, okay? So for example, like we were talking about with the population, if each component is 50% of the total, if it's 50-50, I have the same amount of each, then the ratio is 1-to-1, right? It's equal, okay? Now, if the percentages are not equal, we can still convert that into a ratio, okay? So the way you do it is you divide all the percentages by the smallest one. So let's say my percentages were 25 to 75%, right? Then I would take both and divide by the smallest. So 25 divided by 25, that's 1. 75 divided by 25 is 3. So here I have a 1-to-3 ratio. Okay? So when we're converting percentages into ratios, we always look at the smallest percentage and divide them all by that, and that tells us the ratio. Okay? Okay, so this actually has to do with empirical formula, okay? Empirical as a word means that it is derived from data, okay? So this comes from data. And it is percent composition data that we are going to use to determine the empirical formula. Okay, so that's the data we're going to use to do that. Empirical formulas are simply ratios. And ratios, we know, need to be simplified. Okay, so let's say I ended up with a ratio of 7 to 14. Well, we can simplify that. We can divide both of those numbers by 7. Okay, so we're going to simplify. And if I divide each of those numbers by 7, I get a 1-to-2 ratio. Okay? And so if I have a really large formula with really large numbers, I can take that large molecular formula and we can simplify it, okay, into an empirical formula, okay? And we're going to talk about how to go the other way in just a moment, how to turn an empirical formula into a molecular formula. So the first thing we have to do when we're doing this process, when we are taking percent composition data and using it to derive an empirical formula, we have to start with percent composition, right? Okay. And then the next thing we do is we take the percent. So, you know, in the previous example, we had 24.02% carbon, okay? So what we would do is we would divide that percentage by that element's molar mass. Okay, so if we have a percent of oxygen, we divide it by 16. That's the molar mass of oxygen. We use the monatomic masses directly off of the periodic table. I know that some gases are diatomics, but we do not take that into consideration. Okay, so just use the mass off of the periodic table when you're doing this. Okay. So then you look at all of your answers. After you've taken each percentage and divided it by the molar mass for that element, you will determine the smallest value. So you look at all of those numbers and figure out which one is the smallest. Every answer you get is going to be divided by the smallest value. Just like we did when we converted those percentages to ratios. We found the smallest one and divided them all by that number. That's what we're going to do here. Now there's kind of a step 3.5. Okay, sometimes you will divide by the smallest value and you won't get whole numbers. Sometimes you'll get 1 maybe to 1.5 to 1, okay? The ratio, and this is step 4, is supposed to represent the subscripts of each element in the empirical formula. However, we could not have a subscript of 1.5. Do you see that guy? That would not work out. We can't have you can't have decimal numbers as subscripts. They have to be whole numbers. So when we get values and one of them is still a decimal number, what we have to do is multiply until it's a whole number. And what I could do is I could double that, right? If I double 1.5, it becomes 3. Now if I double that one, I have to, because it's a ratio, in order to keep it the same ratio, I would have to double each of these as well. So my ratio becomes 2 to 3 to 2, and those are whole numbers that can then be used as subscripts, okay? So just be aware, this is kind of step 3.5 over here. If after dividing by the smallest, you end up with a decimal number like that, and it's not within a couple tenths of a whole number, then you have to multiply it until it's a whole number, okay? And then use those numbers as the subscripts in the empirical formula. So, next page. Here's an example problem, okay? So let's say that we need to find the empirical formula, and the compound is 71.65% chlorine, 24.27% carbon, and 4.07% hydrogen by mass, okay? All right, so we have the percentages, so that step's done for us. Next thing we have to do is divide each percentage by the element's molar mass. So 71.65% chlorine gets divided by the molar mass of chlorine, which is 35.45, okay? And that'll give me a number. So let me do that real quick. 71.65 divided by 35.45. And I end up getting 2.02. So that is really close to a whole number. That's really close to the number 2. Okay, so we could just round that. If it's not within a couple of tenths of a whole number, again, you can't round. You're going to have to multiply it until it gets to a whole number. All right, next thing, 24.27, so that's chlorine, right? Okay, 24.27% carbon. All right, so I'm going to take 24.27 and divide it by the molar mass of carbon from the periodic table. So carbon's molar mass, let me put the calculator here, carbon's molar mass is 12.01. So 24.27 is the percent of carbon, the molar mass of carbon is 12.01. I take the percent divided by the molar mass of that element, and again I get about 2.02, which is really close to a whole number, so we'll be able to round that. And then the last one is hydrogen, so I need to take that percentage of hydrogen, which is 4.07%, and divide it by the molar mass of hydrogen. And I get about 4.04 for hydrogen. Okay, so I've got chlorine, carbon, and hydrogen. Now the next step is to figure out which of those is the smallest. Both of these are the same, they're the smallest. So we're going to divide everything by that value. Okay, so when I do that, 2.02 divided by itself is 1. 4.04 divided by 2.02, we don't need a calculator after all. That's 2. So the empirical formula for this one would have 1 chlorine, 1 carbon, and 2 hydrogens. So the formula would be C, carbon usually goes first, Cl, H2. Okay. Okay, so then how is a molecular formula different? Okay, so it accurately represents the number of atoms of each element present in a single molecule, okay? So if, let's, talking about glucose, right? Glucose is C6H12O6. I have 6 carbons bonded to 12 hydrogens bonded to 6 oxygens, right? That's exactly how many atoms of each element are bonded together in that molecule, okay? Molecular formulas may be multiples of empirical formulas, okay? So for example, an empirical formula would be CH. I mean, I can't simplify that any further than it is, but I could have C2H2, okay? That is ethene, by the way. Or I could have C6H6, hexene, okay? So we could have multiples of this formula. Instead of 1 to 1, it could be 2 to 2 or 6 to 6, okay? These would be molecular formulas. I would actually have 2 carbons bonded to 2 hydrogens, 6 carbons bonded to 6 hydrogens, okay? The empirical formula may or may not actually be what the molecule looks like. I will tell you, let me go back to that. I do want to put this in here. You need to write this down. All ionic formulas are empirical formulas. Okay, so you're never going to see Na2Cl2. You're never going to see Na6Cl6. Empirical formulas, ionic compounds are always simplified. And the reason is you don't have nice little molecules that keep to themselves. Ionic compounds form big crystalline structures where positive is lined up next to negative. And so you may have a million chlorines and a million sodiums all kind of bonded together in this crystalline structure. And it would come down to a 1-to-1 ratio. I would have an equal number of each. They would be alternating charge, positive next to negative. But I'm never going to write, Na a million, Cl a million. Okay. Instead, we always simplify ionic formulas, right, to their ratios. So for salt, for sodium chloride, we always have 1 sodium for every 1 chlorine. So all ionic formulas are going to be empirical formulas. Okay. Just so you know. For covalent compounds, however, like the carbon compounds, I mean, carbon, hydrogen, sulfur, and nitrogen make up all living things, right? So between those 4 elements, we can make a billion different substances, okay? Some of them may have the same empirical formula, but different molecular formulas, and they behave chemically differently, okay? So organic compounds, covalent compounds, they have molecular formulas that may be different from their empirical formulas. If we need to take an empirical formula and use it to derive a molecular formula, then step 1 is to determine the empirical formula from data we're given. Okay, so use that percentage data and follow the previous steps to determine the empirical formula. Okay, then we have to calculate the molar mass of the empirical formula and the molecular formula. Now, the molar mass of the molecular formula is usually given to you in the problem. Okay. The molar mass of the empirical formula probably isn't, but if you have that, you can just use the periodic table to calculate the molar mass, right? So then what you have to do is you will take the molecular formula mass, again, probably given to you in the problem, and divide it by the empirical formula's mass. And that gives you some multiplier. That tells you how many times bigger the molecule is than the empirical formula. You take that multiplier and you multiply every subscript in the empirical formula by that multiplier, okay? So using the empirical formula in the previous example, and by the way, that was CClH2, I believe, okay? Determine the molecular formula if the molecular mass is 98.96 grams per mole. So again, the mass of that molecular formula was given to us, okay? So I have that top number for this proportion right here. What I need to find is the mass of the empirical formula. So let me go ahead and add that up, okay? So if I look at the periodic table, carbon has a mass of 12.01, chlorine is 35.45, and then we have 2 hydrogens, so I need to multiply the mass of hydrogen by 2 before I add it to the other masses. And so it has a mass of 49.476. So what we have to do is we have to take the molecular mass that was given to us, 98.96, and divide it by the empirical mass we just calculated, the same way we always get molar mass from the periodic table. And I'm looking at this and I really don't think I need a calculator for this. I think that's going to be about 2. I think 98 divided by 49 is about 2. And so what that tells me is that I need to multiply the subscripts in the empirical formula by 2, that the molecule is actually 2 times larger than the empirical formula. So if I do that, if I multiply all of these subscripts, carbon has a subscript of 1, I double it, so I have C2. Chlorine has a subscript of 1, so I double it, that's Cl2. Hydrogen has a subscript of 2, I double it, and that's 4. So this would be the molecular formula that we would be trying to derive. Okay, so I hope this helps, and I'll see you guys later.